Welcome to the Regents Physics Electromagnetism problem set. The solutions to problems 20 through 26. All right, let's go ahead and get started. 20, a wire is moving horizontally between the poles of a magnet as shown in the diagram below. What is the direction of the induced current? Well, you may recall that the key direction for any of this electromagnetism stuff to take place is perpendicular. So the wire would have to be moved perpendicular to the magnetic field in order to induce a current. Or not, that would be the maximum current. You could move the wire at some angle that's not perpendicular, but one angle you can't move it at is 0 or 180. In other words, parallel to the magnetic field. That's what they're showing happening here, that the wire is being moved parallel to the magnetic field. Therefore, there is no induced current in the wire. Number 21, you move a length of copper wire down through a magnetic field B as shown in the diagram below. We want to know in what direction will the current move in the wire segment. And as soon as the wire is moved in the field, a current is induced in it. Thus, the wire segment is a current-carrying wire located in an existing magnetic field. A force must act on the wire. What will be the direction of the force on the wire? A is the application of the hand rule. If you're doing electron flow, you'd use left hand. Conventional current would be right hand. Let's do electron flow just for practice here. This would be left hand. So your middle finger would be down because you're forcing the wire down. The magnetic field is pointed to the right. Therefore, the direction of the current for electron flow would be out of the page. Your thumb ends up pointing out of the page. If you're doing conventional current using your right hand, then you would end up with the opposite answer. The answer would be that the conventional current moves into the page. Again, ask more about this in class if you continue to be confused with application of the hand rules. The second part is a Lenz's law question. Not hardly any emphasis in the Regents course on Lenz's law, but nice to know that here that, of course, if we put a current through the wire or induce a current in the wire, that creates a magnetic field, and that's going to interact with the existing magnetic field. Well, that's going to happen in such a way that the magnetic field produced by the wire is going to oppose the magnetic field creating the induced current. Very confusing worded law. But here we have a magnetic field that would be disappearing, and what would oppose that would be an opposite magnetic field, an attractive magnetic field. So that means the wire would experience a force upward. That's to oppose the downward force inducing the current in the first place. And again, this one's confusing. If you need more help, ask about 21B in class tomorrow. All right, 22. A wire 22 meters long moves at 4 meters per second perpendicular through magnetic field. An EMF as 40 volts is induced in the wire. They want to know the strength of the magnetic field. So we have L, we've got V, we've got EMF, which is the same as voltage, and they want the strength of the magnetic field, which is capital B. The equation that relates this is epsilon equals BLV, or V equals BLV, same thing. So solve for B, that would be V divided by LV. 40 volts divided by the product of the length, 20 meters, times the velocity, 4 meters per second, gives us a 0.5 Tesla magnetic field. 23. A straight wire 0.75 meters long moves upward through a horizontal 0.3 Tesla magnetic field at a speed of 16 meters per second. That's hauling. Remember that 27 meters per second is about 60 miles an hour. That makes 13.5, about 30 miles per hour. So this wire is moving at about 35, in the ballpark of 35 miles per hour upward through the magnetic field. So you've got L, you've got B, you've got V, and this wants to know what's the EMF induced in the wire. We also want to know the wire is part of the circuit with a total resistance of 11 ohms. What's the current in it? So the EMF is going to be V, or same voltage, or epsilon, same thing, equals BLV. 0.3 times 0.75 times 16 gives 3.6 volts of electromotive force. For the second part, B, we just apply Ohm's law. Current would be voltage over resistance. We got an induced voltage of 3.6 volts, a resistance of 11 ohms. Divide 3.6 by 11 and you get 0.33 amps. 24, at what speed would a 2.2 meter length of wire have to move across a 2.5 Tesla magnetic field to produce an EMF of 10 volts? They want to know V, we know L, we know B, and we know the EMF is 10. Well, again, epsilon equals BLV, so solving for velocity, that would be the induced voltage divided by BL. 10 volts divided by 2.5 Tesla times 0.2 meters gives us 20 meters per second. 25. Primary coil of a transformer has 150 turns. It's connected to a 120 volt source. Calculate the number of turns on the secondary coil needed to supply these voltages. And they want 6, 25, 35, and 6. In order to answer this question, you have to understand how a transformer works, and I'm sure you went and looked this up, being the good students that you are. But just to give a quick update on that, there are two types of transformers. There's a step-up transformer, in which you would take the supplied voltage and increase it, like you see here done in A. And then there's such a thing as a step-down transformer, in which you take the applied voltage, in this case 120 volts, and you decrease it to some other voltage necessary for an electrical device to operate. In our life, the majority of the transformers that we use every day and are familiar with are step-down transformers. Power stations, substations, if you will, you see them positioned around every once in a while. You'll see them off in the distance. There's one over here, for example, off of King Street in Trumansburg. Those are step-up transformers. You know, they have a big fence around them that says danger, high voltage. And so you want to be careful with that. But step-down transformers, like that charge our cell phones or operate our laptops, you know, those aren't operating on 120 volts, yet you plug them into the wall. Well, they have to have a transformer which steps down the voltage to that usable voltage by your device. Here's how it works. Okay, you have what's called a primary coil. This is a ferromagnetic core. And a primary coil wrapped around one side of the ferromagnetic core, and that's connected to your primary voltage. Okay, this would be the power input of the transformer. And the secondary coil for a step down means you want less turns of wire to produce the desired outcome. Let's suppose it's a laptop that operates on 9 volts. And so together the secondary coil produces what's called the power output. Well, what happens here is this voltage over here creates magnetism in the ferromagnetic core. This ferromagnetic core that is now magnetized creates electricity over here on the other side. So you're using electricity to create magnetism on the primary side, then you're using magnetism to create electricity on the secondary side. And that's the concept behind it, a transformer. Well, it's really easy. The number of turns on the primary coil and the number of turns on the secondary coil that are required to do this are simply in the same ratio as your primary voltage is to your secondary voltage. So here we go. We got primary voltage over secondary voltage is to the number of turns on the primary coil to the number of turns on the secondary coil. You can see the ratios are the same. The power input is equal to the power output, which is kind of cool. And since power is current times voltage, you can set up these ratios, these relationships, I should say, of the power input to the power output. From this, you can do any problem that you set your mind to with regards to transformers. So back up to our situation here. This tells you the number of turns on the primary. This is the primary voltage. They want to know the number of turns on the secondary. That would be NS for these secondary voltages. Well, in the first case, it's a step-up transformer because it's increasing the voltage. So it makes sense that we have to have more turns on the secondary than we do on the primary. So just set up your ratio. NP is to NS as VP is to VS. 150 is to NS as 120 is to 625. Cross multiply and divide, and you should get a number of turns on the secondary to the nearest whole number. That's 781. For B, step down, they want 35 volts. So we should end up with less turns than what's on the primary, which is 150. So same ratio, 150 is to NS as 120 is to 35. Cross multiply and divide, and you should get 44 turns on the secondary coil. In the third example, they want 6 volts on the secondary. So 150 is to the number of turns on the secondary as 120 is to 6. Cross multiply and divide, and you get only 7.5 turns on the secondary coil. All right, understandable if you'd put 8 there. Number 26, step-up transformer. There's 80 turns on the primary. It has 1,200 turns on the secondary. The primary circuit is supplied with an alternating current of 120 volts. What's the voltage of the secondary? The current in the secondary is 2 amps. What's the current in the primary? And what's the power input and power output of the transformer? So to do this, same way for A, set up your ratio of turns to voltage. 80 is to 1200 as 120 is to VS. Cross multiply, divide, and you get a VS of 1800 volts. Okay? We know that the voltage on the primary, the power on the primary is equal to the primary and power on the secondary. So 120 volts times IP equals 1800 volts times IS, which is 2 amps as given in the problem. Okay? Divide both sides by 120. And you get 30 amps on the primary circuit. And then they want to know the power input and output of each. So you just go ahead and do your calculations. P equals V times I. And you get 3,600 watts. 3,600 watts on both. And it makes sense they should be equal to each other. All right, that'll do it on the solutions for problems 20 through 26. More to come as we apply these electromagnetic induction concepts to 2 more problems, numbers 27 and 28, in class tomorrow.